Hello, Mr. Lundfesty.
Hey, how you doing?
You still remember me?
Good, I sure do.
What's my name?
Lisa, right?
Got him.
No, it's not Lisa. Oh.
There's too many chains.
I'm Susan.
That's right, because did I have your... I had 2 that year. You guys like fought all the time, and I can't remember the other ones.
You had Pamela, but she dropped out of your class.
Were you guys related or no?
Yeah, me and Pamela are cousins.
Okay, because you guys like fought like sisters.
No, yeah, Pamela's my cousin. She's the one who leveled down.
That's right. Okay. So where are you going to college at?
I'm going to Yale.
Yale. Nice. So online education at Yale then?
Yep.
Oh.
Yep. I just got done with my classes.
Oh, you're all done for the year.
Yeah. This is my brother.
Nice.
How's Kobe?
Kobe? He's a little brother, right?
Yeah, he's my little brother.
Okay.
He's a lot better at physics than me.
That's right. That's right.
You're pretty good too. So
No, I barely passed the exam. I'm not on your wall.
So are you the oldest then?
No, I'm the middle child.
Middle child, okay.
Yeah. Yeah, I think next year you might get our other cousin. Her name's Carly.
Okay. Okay, we'll be starting here in a minute. It's good seeing you. Bye.
Yeah, it's good seeing you.
All right, leave.
Bye.
See you, Susie.
Okay, I'm going to start putting you guys in groups. So give me a second here. Okay.
Kevo. Jack, I got you.
Okay, give me a second. I'm still putting people.
Michaela?
She's not feeling it.
She's feeling me. You're right.
Hey, Mr. Lundfesty, are we gonna start reviewing anytime soon, or we're gonna keep doing this magnetism stuff?
I'm probably going to talk a little bit because here's the thing. They have not been very specific exactly what's going to be on your test. In fact, I was going to tell you that tomorrow night at 7 p.m. I'm going to attend a AP meeting that's going to talk about that. So the College Board's going to be putting on. And so I'll be able to share a little bit more with you. They've only released 3 problems that we could use to review. So, and those problems aren't even that great because they're a format that we've never really seen before. So, I mean, we will start to talk about a little bit. I mean, we're pretty much done with this section. So kind of like after Wednesday, that's kind of the end of the new stuff. And then we'll have next week to review too. So.
All right, sweet. Okay. Stuff makes you want to drop the class.
Oh. Guys are breaking my heart. Okay, wait a second. Who am I missing here? Brendan, Ben.
We gotta get outside.
Joe won't be here. He's got a meeting with I don't even know, someone. He won't be here.
He helped us with the whiteboards though, so he should. Yeah.
Almost under.
Okay, I think I've got everybody in a group, but some people aren't here yet. So, okay. All right, I'm going to go ahead and get started. So let me share my screen with you. So yeah, I was going to share with you that the fact that I'm going to attend this meeting tomorrow, Tuesday night, and then I'll know more to tell you on Wednesday. I'm also going to assign those 3 problems then for you to do because you don't have any more internet homework. I'm going to assign those 3 problems for you to look over the weekend, and then we'll have the following week to talk about them. The truth is, though, if you've been doing the internet homework, the circuitry problems, the electrostatic problems, Gauss's law stuff, in theory, you should be set for the test. It should be, I mean, every one of you should get 5s, assuming the test is fair. So I don't think if I were you, I'd be worried about it, because what can you do about it if it's not a fair test? Like if it's a totally different format or something. My thinking is they're probably going to be generous in the grading. So I really think that this is probably going to be the highest scores that I ever had, just because it's not going to have any magnetism stuff. It's only circuitry and electrostatics. And this is all kind of new on the computer and everything. So I think you guys should do really well on it. So anyway, all right. So what we're going to do today is we're going to be whiteboarding the electrostatics lab. And the electrostatics lab, what you were doing was some simulations. The first one, I asked you to watch a video that kind of helped you with this part here. And let's see, what do I want to do? Yeah, I think I want to give you a couple minutes maybe to get in your whiteboarding groups. Unfortunately, some of you, your partners aren't here. So anyway, I'm only going to give you a couple minutes to kind of do what it says here for this one, to write a purpose statement, draw the needle direction, and all that kind of stuff. All right, so let me see if I can, okay, wait a second, what's going on here? Stop sharing. All right, so let me go ahead and put you into breakout rooms. Riley, unfortunately, your partners aren't here. Miranda's partners aren't here either. Do you want me to kind of put you in her group, but you're going to do your own whiteboards? I can't hear you. You want to unmute yourself?
Sure, Mr. Infesti.
Okay, I'll do that. All right. Okay. Question.
Yeah, so we're just trying to figure out that question. Why does the galvanometer needle move? And you said it wasn't the magnetic field.
Right. Okay.
Right.
So I don't see a magnet there. Do you see a magnet?
No.
Okay. So you can't say that the needle moves because of a magnetic field. Now, I mean, I agree that there is a current that is created, and then that current that then turns or does create a magnetic field. But then you kind of get a chicken and an egg. How can that magnetic field cause the current that caused it in the first place? So
Okay.
I don't think that's what's going on there. So, I mean, do you agree that there's a current going through the wire?
Yeah.
Yeah.
Okay, so it kind of looks like that needle is kind of indicating that there is a current, right?
hmm
Okay, so the only thing is, does it point in the direction of the current?
No.
No. So really what it's doing is it's actually kind of showing you which one, if you're thinking of color coding, it's kind of pointing in the direction of the one that's a higher potential, the higher. So that galvanometer, what it does is it really is pretty sensitive at measuring voltages.
Oh, okay.
So it's measuring the voltage, the potential across there, and it's pointing to the high potential end.
Okay.
Does that make sense? Okay, all right.
Yeah.
Hey guys, are you guys looking at your whiteboard?
Already done with it.
Yeah, but I need you to look at it.
I mean, it's kind of wrong, but it is done.
Because I
Yeah,
gave you a note there in the margin. So
oh yeah, we even forgot to get rid of the right-hand rule.
so what does the right-hand rule have to do with anything?
Nothing. That was just we put it in there to have an answer that we forgot that we put it in there.
Okay, so first of all, your needle is all wrong. Did you guys watch the video?
Couldn't find it.
What do you mean you couldn't find it? All right,
Couldn't find it.
all right, so let me share my screen with you.
Must have
So,
skipped over.
because we're gonna watch it right now.
Gotta find your screen.
All right, so, all right. Okay, so last week on Wednesday, here's the, oops, no, here's the, is that it? Yeah, this is the one, I believe. So watch the needle. Now I flip the battery.
It goes against the current, like right into it.
Yeah, so it's not pointing in the direction of the current.
It points against it. Because it points in the direction of, I forget how to phrase it. I don't know when to phrase it.
Well, I want you to think about color coding. What is it telling you?
Pointing to a high. It's pointing towards higher voltage.
That's right. So it's really kind of measuring the potential, the voltage. So whichever one's the higher voltage one. So fix that, please.
Mark, fix it. I'll fix the right-hand rule. Just kidding, Mark. I love you.
Oh, I don't know.
So Miranda, did Kylan talk to you about why she wasn't here today? I think she was having surgery or something. And I think
Oh.
that's what yeah. So remember she had something wrong with her knee or something. So,
Oh yeah, that's right.
So that's why.
Okay.
Okay, so I think I went around and I looked at everybody's whiteboard. I don't know that I looked at all the answers to make sure they're all correct or anything, but let me kind of just share this one. Let's pick one here. Actually, you know what? I think I'm just gonna open up a blank one and we'll go over it together. Okay, so first of all, it should have been really easy to draw in the direction of the flow. So the flow, conventional flow would be down like this, be up on this side. Over here, it'd be down on this side and like this. Across the galvanometer, it's gonna go kind of like that. And it's gonna go across here like this. But what did you notice about the direction of the needle?
Backwards.
Is backwards, right? So in other words, the needle for the one on the left is kind of pointing towards the opposite direction. It almost looks like it's pointing the opposite direction of the flow, but that's not really what it does. The galvanometer is not really telling you about the flow. I mean, is there flow? Yes. But it's actually telling you something else. I want you to think about color coding. What is it telling you?
Is it telling you voltage?
Yeah, it's kind of like telling you voltage. Which one's a higher potential? And so the reason why the galvanometer needle moved is because there was a pressure, well, there was a voltage across here. And so that's why it was moving like that. What information does the needle give you about the current? So if there is current flowing, we always know it flows from high to low. So it's telling you kind of where the conventional current is flowing into. Okay. All right, so the next one we're looking at is part B. And this one's kind of interesting. I hope you took some time to look at the simulation for this. You have to do a lot of things here. First of all, for one of the loops, let's see, can I zoom in? If I can zoom in. No, I cannot zoom in. Dang it. That's backwards. All right, so I'm zooming in by, that's weird. Okay, so for one of the loops, so for instance, if you're looking at maybe the picture over here on the left, the upper left, I see a bunch of parallel lines. Those represent loops. On one of those loops, you should draw in the conventional flow. But I recommend, well, actually, you should be able to do that because you saw what the meter did. So that should be pretty easy. And then what I'd like you to use is the right-hand curl rule to figure out the direction of the magnetic field through that coil. That will help you figure out which end of the coil is north and which one's south. So you're going to have to label in the direction of the flow, label in the direction or the north-south of the coil. And I'd like you to do that for all 8 of those. After you do that, you should be able to figure out what does the needle tell you, or excuse me, what does the needle do if the magnet is just held in place. I think you could do that one too. Yeah, you just stick it in there. I think so. You could figure that. That should be easy. And the one I want to spend the most time on is trying to boil this all down into something that we can use. So this might be hard. I don't know. So let me stop sharing, put you in your breakout rooms, and give you a few minutes to do that. Okay, did you see that I left you a note on the picture there?
Yeah.
Yeah.
Okay, remember how we said the needle points, it's kind of like looking at pressure, or the high pressure.
Oh, yeah.
So the flow would be the other direction. I think that's the only thing, I didn't look at the whole thing, but that's the only thing I saw. And I think you had consistently that was wrong for all of them.
Okay.
Okay.
So the current was the other direction. Yeah.
Okay.
Flow, it comes to the meter on like,
Which parts are you saying that are wrong, Mr. Lenfesti?
Okay, so do you remember how in the last part we said that the meter kind of tells you where it's kind of looking at pressure,
Yeah.
the high
Mhm.
pressure, right? So your
Yeah.
needle on your meter is totally right. That was totally right.
Okay.
okay,
So that means you have this, I'm going to highlight it there. Do you see what I'm clicking on right now, that arrow?
Yeah.
yeah,
That arrow is not correct because it's got to be going down into the meter, which means that this is actually, oh,
Going
shoot.
up.
Yeah, let's see. I could just change the direction. Here we go.
Yeah, you could just flip it around.
This will work. Yeah, like that. So it's actually going like this, up.
Okay.
okay, that makes sense.
And
And
then,
this one would be going down.
yep, exactly. Yep. Okay.
Okay.
than the car itself. Fantastic.
Okay, so I pulled you out of your whiteboard group because we're kind of having a problem in just our observations, and it might be the simulations I gave you. So I'm going to see if I could find something better. Okay, so let's share the screen. Let me get away from that. Let's see. It's starting to be a little bit difficult to find decent enough simulations. I think I'm actually going to have to click on the next simulation to help find something decent. Let's see, which one was it? It was that one there. Do you mind muting yourself? Could everybody mute yourself? Thank you. Okay. I hope this works. I'm not even sure if this simulation exactly matches the picture, and that's the problem that we're having. So even this doesn't match the picture exactly. So here's the picture that we're looking at. Notice the coils, the way they're kind of slanted up toward the left. And the simulation here that we're looking at is they're kind of slanted to the right. So this is still kind of problematic. So you've got to really be thinking here, because this is a three-dimensional problem that you have to kind of imagine. So first of all, it was really, I'm going to show you that some people are saying, if you look at this first one, let's look at the upper left. Some people are saying that we had the needle point to the right, but then we'll have other groups that have it pointing to the left. And that's the problem we're having right from the get-go. And we can't have any kind of consensus until we find out, you know, what's going on there exactly. So I think it's just something we're going to have to talk about instead of trying to get consensus. It's too difficult. So I just want you to watch this. Notice that when I have this North Pole come into this, I've got this thing kind of moving, deflecting toward the right. So let me go ahead and I'll have it go in again. Notice the needle deflects towards the right. So I want you to think about the observations we just said. So here in a second, I need you to unmute yourself. If it deflects to the right, what does that tell you about the flow across the meter? Is the flow across the meter from left to right, or is it from right to left?
Right to
Right
left.
to left.
Right to left.
Okay, good.
Left.
So we all agree right to left. So this is the part that's a little bit difficult. So do you see this coil? Can you guys see my cursor when I move my cursor?
Yes.
Yes.
Yeah.
Okay,
Yes.
so you see this coil all the way on the left-hand side. Imagine grabbing it with your right hand. In fact, you might want to pick this up right now. And your thumb has to be pointing kind of down and toward the left. Okay. Wait a second. No, I did that wrong, right? Because it has to be, because that'd be going in the wrong side. Sorry. It has to be pointing up and to the right. Sorry, I was doing it wrong. Up and to the right. So what's important that I want you to see is imagine that little loop, that loop on the end. If you grab it such that your thumb is pointing up and to the right, then that would cause a current across the meter that would be from right to left. Do we all agree? Give me a thumbs up if you agree. Okay, here's the important thing. Think about the way your fingers are going through the middle of that loop now. They're coming out. Can you see that your fingers come out the left end of the coil? Do you agree? Okay. If that's true, what is that pole? What would that be? Would that be a north or south pole on that coil?
South.
So they're coming out of it. How do the field lines, do they?
North.
It'd be
Yeah,
north.
It's actually, yeah, it's north. Now, what's confusing about magnetic fields is on the outside, it comes out of the north, but on the inside, it comes into the north. That's what's confusing. Okay, so I want you to understand that this left end of the coil is north only when the following happens. When I bring this magnet into it, it creates a north pole there. So let me do it again. It created a north pole right there. Now I want you to see what happens when I pull it out. Watch the needle. Oh, shoot. Come on, let me try it again. I'm gonna pull it out. Could you see it? I don't know if you could see it very well. Which way did it deflect? Which way did the needle deflect?
Left.
Yeah, and so if you go through the right-hand rule again, you'll say, okay, now my thumb has to point down and to the left to create that current through the meter, which now my fingers will enter, and it enters on the south end. Okay, so I want you to really think about that because that's neat about nature. When I bring this north pole closer to this coil, it will form what kind of pole at the end of the coil?
North.
A north. And when I pull it out of the coil, it will form what kind of a pole?
South.
A south. That's very interesting because I want you to think about it. When you try to bring that north pole into it, what is it kind of doing? Is it helping you or is it resisting you?
Resisting.
It's resisting, right? So when I bring this north in, it forms a north. It's trying to say, hey, no, I don't want you to do that. Get that north pole away from me. And then once it's in there, it's saying, hey, I like this. Don't go anywhere. And it's trying to pull it back in. That's really important about nature. We just found out nature are Republicans. They don't like change. Okay, anyway, no, so seriously. Okay. So it doesn't like a change. But that's true. It doesn't like change, but there's a reason for it. And here's the reason. Is because look at remember the direction of the needle? It was to the right. If it would not do that, let's say it would have formed, let's say a south pole. So when I bring it here, instead of being a north pole, let's say it formed a south pole, then it would automatically attract it. It would actually get faster. And so there would be more current. So in other words, the reason why nature does that is to conserve energy. I actually have to do work to get this to create a current. So I don't want you to think, hey, you can get free current here by moving this magnet through. Yes, you can get current, but only at the expense of your energy. That's where that energy is coming from, that electrical energy. Okay, so any questions? Because then I want to go back to the lab sheet. Okay, let me go back to the lab sheet, and I'm just gonna, whoops, wrong. Get rid of that. And I'm just gonna pull up one since that didn't work so well. B. So I want you to understand that when I'm doing these problems, the way I think of this is, oh, there's a north pole trying to come into it. Over here, I'm looking at the far left. That means this pole is going to create a north pole. This coil is trying to resist it. And now what I do is I use my right hand and I grab that farthest left coil. I have to imagine it. You have to think three-dimensionally. And my thumb is pointing upward on that coil. So in other words, the current is going to be like this. It's pointing upward. And that creates a current across the meter this direction, which causes the needle to point that way. So then the next one, again, nature does not like change. It's a big fat Republican. No, I'm somewhat of a Republican, so I'm joking here. So anybody's Republican, please don't take offense. I'm just trying to get a picture in your mind. It's conservative, okay? So south, that's a south pole, right? And so again, what I do is I grab this with my right hand, and I need to create a south pole. That means the field lines, my fingers are coming into it. So then the current is going to be down like this across the coil, which means that the flow is going to be this direction, which means the needle on the meter is that way. Okay, I'm not going to do any more on the top row because I want to jump down to the bottom row, because you might look at these and go, oh, it's the same thing. But notice how the coils are slightly different. That's a big deal. So still the same thing on the far left. That's going to be a North Pole. Nature doesn't like change. That's a North Pole there. So how does it create that North Pole? Imagine grabbing that far left coil. You have to have it so your fingers are coming out that end, which means there would be a flow upward like this across one of those coils, which means there's a flow this way across the meter, which means the meter is going to deflect that way. Does that make sense? Okay, let me do one more here. So we're trying to pull this way. Nature doesn't like change, so this is going to form a south pole over here. And imagine grabbing, you could grab any one of those coils. It doesn't matter on that coil there. I'm going to grab the far left one. I think it's easier for me to imagine. And so I have to grab it so my fingers are coming into that end. And so my thumb is pointing down along that wire there, which means the flow across the meter is this way, which means the needle deflects that way. Okay, could you guys unmute yourself for a second? What did the needle do when the magnet wasn't moving?
Nothing.
Doesn't move.
Back to the middle.
Doesn't move. Doesn't move, right. Okay, so let's see if we can do this together. This is going to be kind of hard. So let's see. I don't know. This might be too hard to expect from you guys. I think I'm just going to tell you. I think it'll make sense though from you. First of all, remember these galvanometers. What were they indicating? It wasn't indicating flow. What were they indicating?
Potential difference.
Yeah, voltage, a potential difference. Yeah, kind of pressure. So what's happening is that in order to conserve energy, nature creates a voltage that it then in turn creates a current that then in turn creates a magnetic field to oppose the change. That's what's going on here. So let me just pick one of these here at the top. It's really interesting. So to conserve energy, we know there has to be a North Pole here to oppose the change. So that means you had to create a voltage, a pressure difference, that then created this current, that then created that magnetic field to oppose the change. So let me see if I can write that all down. To conserve energy, an electric potential is created that then in turn creates a current that then creates a magnetic field that opposes, I don't think I spelled that right, opposes the change in magnetic field, in the magnetic field. So nature doesn't like a change, and so it's going, because in order to conserve energy, and so therefore it's going to create a situation where it's harder to change the magnetic field. That's what's going on. So that's kind of confusing. Any questions? I could try to see if I could say it again or in a different way if it didn't work. All right, so the next one we're going to do is part C. Oh, I think this one will be easier. Maybe we could do this one together to save a little bit of time. The bigger the movement of the needle on the galvanometer, the larger the what in the coil?
Current.
Yeah, the current, right? To create the current, though, you also had to have a voltage. So I'm okay with either one of those, a greater current. Yep. Experiment with moving the magnet in and out of the coil, first slowly, then rapidly. What'd you notice about the relative strength of the current induced?
The factor that you went in and out.
What happened with the faster?
The current got higher.
Yeah, I agree with that. That makes sense. Everybody, is that what you guys saw? It kind of makes sense. It's logic. I'm hoping you're thinking about energy. If you're doing this faster, then that's probably more energy you're putting into it. Okay, compare the induced current caused by the magnet as the number of turns. So I think that you could see that in that one simulation. I think you were able to, if I remember, I think you could. Wasn't this simulation where you could change the number of coils, I think?
Yeah, you could change it up to 3.
Yeah, okay. All right, so for this one here, let me go back to that. What happened when you had more coils?
There was more flow.
There was more flow? Okay, did everybody see that? There's more flow, okay. Compare the induced current caused by the magnet as the magnitude of the magnetic field changes. So I think one of them you could change the magnetic field too. What'd you guys see?
Proportional.
So what do you mean by that? So in other words, as the magnetic field got bigger strength, then you found what?
The current went up.
Okay, is that what you guys saw? Makes sense too, I think. Okay. Compare the induced current. Oh, this is the one where instead of moving the magnet, I think you were able to also move the coil. So what did you notice in that case? Did you guys see anything?
They were equal.
Yeah. So it doesn't really matter if the magnet moves or if the coil moves, as long as there's some relative motion. So if they're doing this, I don't know if you can watch me for a second. If they're moving together, so there's no motion between them, the relative motion is 0, there won't be a magnet induced voltage and current. It's only when there is a relative motion between the two. Good. Okay, then the last one, the conclusions. I think this one we can kind of do together too. Let's do the direction last, because again, that was kind of the confusing one. What are some things you can do to change the magnitude, though, of the current?
Increase number of loops.
Having more loops. What else?
Higher speed.
Have a greater speed, a relative speed between the two.
Bigger magnitude of the magnet.
Bigger magnetic field, right? There might be other things, but those are the only things that we could test. Okay, in terms of figuring out the direction, that kind of comes back to the first one that I kind of said over here. To figure out the direction, to conserve energy, an electric potential is created that then creates a current, that then creates a magnetic field that opposes the change in magnetic field. Reminds me of like Russian nested dolls, or remember that story you heard when you're like in elementary school, the woman who ate a fly, don't know why, and all that. You know, that's kind of reminds me of that one. So, any questions about this lab? So let me go back to, boy, I'm going really long today. Okay, oops, wrong day. I would like you to kind of finish this up and turn it in by midnight. So as far as turning it in, I've already got the file. So all you have to do is complete it. And you have it completed and there, it's turned in already. Okay. Let's see how, oh my gosh, we're already at 50 some minutes. I don't think we're going to do either one of these things then. I don't think you can do this then. I don't think we can do the attendance quiz. That means I just want to get the picture from you guys then. All right, so turn on your camera so I can get a smiley face. Yay. All right. Okay. Okay, so There won't be then an attendance quiz. I don't think you can do it since we didn't do the other problems. It went a lot longer than I thought it would be. Sorry about that. I will give you more information about the AP test then on Wednesday. And I will probably assign like 3 problems over the weekend that are AP problems, and we'll discuss them next week then. So any questions? Okay, that's it. Thanks for coming. See ya. Bye.